we will resume the session from where we left yesterday. So, just to summarize, we did touch upon various aspects of what is machine learning, what are the various types of machine learning, how exactly you do a learning, what aspects make you to categorize them as supervised, unsupervised, reinforced. Then we did happen to come and speak about one other aspect of the learning quotient, where we say we happen to use the classification, the clustering, the anomaly, and regression. So if you happen to see it from a very broad perspective, the highest level of learning can be categorized under three, which is your supervised, unsupervised, and reinforced, while the areas such as clustering, classification, anomaly, regression are the subveins which happens to roll up to your mainstream of learning quotients. With that, if we come to the area which we will have to talk more, is all about regression, right? So regression, by the name it says, right? So many people with a background from statistics already understand the word regression, but we are leveraging the same statistical principles into the area of machine learning, and all that we are trying to do is the heavy lift activity in any regression analysis is the calculation. So we are leveraging the technology part to do the heavy lifting activity of calculation and enabling the whole aspect to help us to influence to make a decision. So if we have to circle back, what is this regression? Typically, you can define regression analysis is a form of predictive modeling technique which investigates the relationship between a dependent and an independent value. So, like we were picking up various examples, whenever we have to predict something, we basically have a relationship with some other variables. So, for example, if I say, when will you get hungry? Assuming you are not hungry now, if my question is when will you get hungry, you will say probably by lunchtime, by snack time, or by dinner time, which means you are factoring a variable of time and saying that your forecast for getting hungry will get associated with that. Or if I ask you, how long will you take to reach your school or a college or an office, indirectly you will happen to use a parameter which is the distance, the time of the day, the mode of transport, which means these are the three independent variables which is impacting the duration of travel to your office. For example, if you say your office is 3 kilometers from your home, the time of travel depends on whether you walk, you take a two-wheeler, you take a four-wheeler, you take a public transport, and what time of the day and what week of the day. Which means these are all your independent variables, while the dependent variable, which is the time taken to travel to your office, is having a relationship on this, which means when other variables or the independent variables change the dependent variable has an impact which we call a function, which means, for example, if the distance is 2 kilometers on a Monday morning using a car, if the travel time is 5 minutes, if the distance becomes 6 kilometers on a Monday morning using the same car, the time of travel will change because the distance changed, which means the independent variable changed and the dependent variable will have an impact, and we do the same. So basically we try to find the relationship between a dependent and an independent variable, and using that relationship we try to arrive at some predictive quotient that is called as regression. If this is regression, let's see how exactly regression we use. So basically there are various things in our day-to-day conversations we use regression without explicitly identifying it as regression. So as simple as if you are planning to buy a house in a given locality, the price of the market price of that particular house is a function of so many other attributes: the locality, the house size, number of bedrooms, so many factors, right? The combination of all these independent variables will influence the price of a given house, which is the dependent variable. Similarly, you also try to forecast the weather. It could be what will be the temperature of a given city for a given day, probably tomorrow, day after, or you also try to predict will it rain or not rain tomorrow, which means that is also a kind of prediction. And if I ask you that question based on today's weather and what you have seen previous days weathers, you try to forecast it for the next day, which means data itself is predicted because we have not seen tomorrow. We try to predict based on the information what we carry. So on this particular things, the whole regression approach is based up on. So if you see what will be the temperature tomorrow, or how much discount can you get on a particular item, are all your quotients of regression. So if you happen to see in Python, since you guys have gone through the basics of Python and you would have a fair understanding of modules, libraries, functions, all of this, there is a very, very evidently used library within Python, which is called as scikit-learn. Like you would have used pandas, you would have used numpy, you would have used matplotlib. So numpy is for your metrics calculations, pandas is for your exploratory data analysis, matplotlib is for visualization. Scikit-learn is a library which is having a rich inventory of algorithms. The algorithms, like we already discussed, an algorithm is an approach, and each of this approach, what we name, will have a code which is readily available for you to consume, and you can go ahead and use it. So always whenever you are using a library, it's a very good practice that you go to their documentation and see what exactly you have. So if you type scikit, so all these libraries are very vast libraries which are available. So if you see scikit-learn.org is a web page which has a exhaustive documentation for all the aspects what we go through. Now, whatever we discussed, like a classification, a regression, a clustering, which we will try to talk, all of this have a section on their documentation. Now, if you go into our area of interest, which is regression, so there are various ways of regression which is available. We will talk on that. I'm just showing you how to find, where to find, what is the resource approach, because everything can keep changing, but if you know the way to tackle and handle, it becomes relatively easy. So if you see here, under supervised learning on my left hand side, you have linear models, kernels, nearest neighbors, neighbors. These are all the supervised learning algorithms what we have. Within that, I have selected the linear models within supervised learning. This basically gives you the entire list of algorithms which are available in this one library, scikit-learn. Okay, so if we select on the regress, we can go ahead and see the whole concept of how exactly the whole regression works. But we will see this in detail in our description and in our discussion now. But whenever you are trying to use any library or any function from a library, make it a practice that you know where the documentation is, what the documentation says, and for a given function, how many attributes are available, how many attributes are mandatory, how many attributes are optional. That way, you are using the function very well. Otherwise, you might be underutilizing the function or trying to overutilize the function. So, to reduce that aspect, make it a practice to see how and where and what are the various options available. So, it is like this: whenever you buy a new gadget, it is always suggested to use the read the user manual before using it. It's a simple practice, right? You will know what are all the do's and don't do's about a particular gadget. This is also on the similar lines, and if you spend some time, you will see the mathematical formulation whatever they have used because at the end of the day, a function is a program written in a fashion which can consume some variables or parameters and give you the written result, right? So they have spent good amount of time in doing this. Now, the pictorial representation of the scikit-learn is this diagram. What is this telling? This is telling us when to use what kind of algorithm, right? If you see, this is an scikit-learn algorithm cheat sheet. What does a cheat sheet mean? A cheat sheet is a quick reference when you are deciding something. So a lot of effort has been put into developing this cheat sheet. And if you see, there is a start icon and it says if you have less than 50 sample data, don't even proceed further, go ahead and get more data. If it is more than 50 sample of data, then see based on the category of the data. If the data is labeled data, we understand what is labeled, right? I explained you yesterday when we were talking about supervised algorithm, labeled data. So if the data is labeled, then you can get into this section. If the data is unlabeled, get into this section. If the data is labeled less than 1 lakh samples, then you can look at linear support vector algorithm. If it is greater than 1 lakh, then go for SGD classifier, which is a classification approach. If it is a linear support vector and if it is not working, look at the text data, which means there has been a good amount of thought process which has been put. And if you ask me, is it 100% right? The answer is no. For a simple reason, every data is very different. This only gives you the industry best practice to say what to see where and how to navigate it through to make the things more reliable. Right? So that's how, if you see, if it is not a labeled data, you go into clustering. If it is on the quantity, go on the regression. If you are looking for something more, the data is heavy, try to go on the dimensionality reduction, where we will try to talk about principal component analysis, all of those. Right? So the whole machine learning algorithm approach, what you get to see, has been put holistically in one diagram. Since we are talking about this, let me quickly see if I can project the list of algorithms what we have in the whole machine learning. And it is never a static thing, it is always a changing thing. But let me see if I have that. Okay. I think I don't have it here. Okay, let me pick that up and I will show you. But the whole intent is, one second. Okay, so the whole intent is basically whenever you happen to have a data, how exactly to navigate it. Okay, so that's the whole approach of a machine learning cheat sheet. But if you also see, this is one other cheat sheet for machine learning. So if you happen to say we are using a regression approach, we have a regression, logistic regression. Then if you happen to say decision tree or model validating matrices or support vector machine or neural network, how exactly to use a library, we have made this particular things. right? So that way you get a handy information in terms of where is what. Okay, so with this, let me get into the area where we will try to talk about in the one of the regression types, which is the logistic regression. And I understand linear regression is something which has been already discussed, and you happen to have seen the example of how you use linear regression. So, just to get that point of continuity, if you happen to say, what is the temperature of a given city tomorrow, the prediction can be anything. It can be 33.25 degrees centigrade, 33.16, or 40 degrees centigrade, or 23 degrees centigrade, whatever it is. Which means the prediction of such things which is continuous in nature, you can use your linear regression. So, if a prediction has to happen on a variable which is continuous in nature, linear regression suits very, very well. But let's imagine I ask you a question saying, will it rain tomorrow? My question is simple. Will it rain tomorrow? Your answer can be only yes or no, right? Which means your answer to this question, which is again a prediction because you have not seen tomorrow, you are trying to predict, but the prediction is not continuous. The prediction is discrete. What do you mean by discrete? Here, the options for predicting is only two, yes or no, which is logical in nature. So, whenever the prediction has to happen for discrete items or logical items, you need to go with logistic regression. Linear regression will fail. So let's see how exactly or what exactly is our linear regression, how exactly they fail. So what I will do is I will show you a data set. Let me bring up a data set. Okay, so if you see, my file name is product sales. Very, very simple data, which means I don't have a lot of columns, only a lot of rows or two columns where I have the each and a column telling me bought as 0 and 1. So if it is 0, he or she with the age group what is defined in column A has not bought a product. If the column B has a value 1, whatever the age of a person which is in column A has bought a product, which is a very, very, very refined data. I've taken this simplistic data so that we understand how exactly we use logistic regression. Now, if I see this particular thing, let me pull up my Jupyter notebook. So, hope all of you are using one or the other types of IDE, and let me pull up this Jupyter. I use Jupyter notebook. So my Jupyter notebook is just loading. Give me a second. Oh, I will go open a new file so that I have a new editor for my logistic regression. Okay. Now, for this logistic regression, the first what we will see is how is this logistic regression a valid approach for predicting something. So what I'm trying to do with this data, I will tell you. My goal is, I have this data. We saw that there are 300, 400, 500 records, 458 records of various age groups of people who have visited my store. And I have calibrated and configured the data collection, saying that based on the age, I have determined whether they have bought a product, they have not bought a product. Now, my intent is to see if a new person of age 25 walks into my store, whether he or she will buy a product or not buy a product, not buy a product based on the previous experience. So that's what we will try to see. Now, if I see this, now what I will do is, basically let me show you that I am first importing my data which is available here. So I have imported some libraries what I need. I have imported my NumPy library, my Pandas library, my Matplotlib library. Then I am importing my library where I have the file which is available for me to consume, which is the product sales dot csv, right? Let me see what was there. Okay, let me increase so that you are able to see. Okay, let me change the path where I have my file, a relatively longer path. Let me take that. Okay, I have it in my stored in my e colon. So I'm just putting my path. Okay, now once I do this particular thing, if I run this particular thing, like all of us know, whenever you see a star, this is in the computing mode, which means it is reading the data. When it completes, this has a number. It will say in1 because the first input what it is running. Now it will say in1 or it will give me an error. Now it did not give me an error, which means this particular block of code was successfully run. Now, if I see my sales data frame, assuming all of you understand the Python pandas, I am just running the data. So if you see, I have my data which we just imported. So we have the age, we have the bot, which is the data what I had in an Excel file. I just read the data into my Python. Now, always it is a best practice to see if my data is the right data. So either you can see the complete data frame or you can see it using some of the options, like if I say sales.head, it will give me the first 5 records of my data. If I use the tail, I'll get the last 5 records of this. And if I use sample, any one record it will give. Inside this, if I say 10, it will be give me randomly 10 records. If you see, this is the row number 382, 373, 336, 112, randomly 12 records it will pick and show me what are the values which are available. So that way, because always why is it is a best practice is, you have fed the data, it becomes very easy if you cross verify whether the data what you loaded and what you are going to work is it same. So always make it a best practice to use this. Now we will see what are all the values by its headers. So we have anyway two in this data. It is very small, only 2 columns. But if you happen to see, if you use the columns dot values, it will tell you we have 2 columns. If you have a data which is large, it is always good to see whether all the data across the columns have been loaded or not loaded for whatever the valid reasons. Now, what we will do is, since most of you have already attended the linear regression, let's try to see using the linear regression what will the result look like. So I am building a predictive model for bot versus age. uh, Whether a person of what age has bought a product or not bought a product. So let me copy this code. I will show you or read what this that we are trying to do. Now in my first block, all my mandatory libraries are imported: NumPy, Pandas, visualization for your visualization, Matplotlib. Now I am importing the machine learning specific library which I'm going to use, and in this case I am importing a library called a stats model. Stats model is one other library like ExcelR which has various functions for various algorithms, and it is a statistical rich library. So what I have done is I have imported stats model as an abbreviation SN, so that I don't have to really write statsmodel.api always. So I have abbreviated it with a smaller name. Now I am using the ordinary least square method of linear regression. Hope you have read about OLS, or the least ordinary least square approach. So from this library statsmodel.api, I am using this function, and for that function I have to pass two attributes. And anyway, in my data I have only two attributes, age and bot. So sales with bot, and I am adding a constant. Along with that I am adding the age. Then I do the fitment, which means I am doing the model fit. Once I do the model fit, I will also get the summary. What does summary tell me? Summary gives me various parameters about a given algorithm. So for example, while reading linear regression, you would have gone through something called as R square, adjusted R square, which are an yardstick or a metrics to measure how good that particular function is, or how relevant the prediction is coming for a given data. So all these particular things are immediately given by this summary. Now let me go ahead and run this particular thing. Now all that it is doing is it is consuming the data which is available in the data frame, putting it in your X and Y, then calculating your linear regression and giving you the summary. So if you see this, this is the result of summary. Your R squared value is 0.84. In terms indirectly or directly, you can say the linear regression for this data is relatively better. Anything above 0.8, you can still consider that to be very, very good. Now, if you see the linear regression result says 0.842 of R square, adjusted R square, coefficient, standard variation, p-value. These are all few things which are available as a metrics for you to see how good this algorithm for the given data. Now that we have the results of linear regression, let's try to go ahead and predict whether a 4-year-old person will buy a product or not buy a product. So I will go here. I will say if a age is 4, then that customer will buy the product. We are having on a variable age 1 as 4. From our model which we fitted above, we pass the value age 1 and then we try to predict. Now if I see this particular thing, it is telling me a value minus 0.086. What can I conclude out of it? I told 0 means it is not buying, 1 it is buying.
Now it is telling me minus 0.086, which is below my zero value, a negative value. Theoretically, I cannot conclude anything. When it is minus zero, should I say that the 4-year person guy will walk into my store, he will pay me money and go out of the store? That is what zero tells, that is what minus number tells me, right? If it is zero, he is walking out without buying. If it is minus, he will pay me money for not buying anything and go. Not a right approach, right? Let's see with one other age, thinking that if this is uh, really right or wrong. Let's see if the age is, I will increase the age to 105. Same code, I have increased the age to 105. Let's see what it tells me. It is telling me 2. The result is telling me 2.02. But we said our value should be between 0 or 1. 0 means not buying, 1 is buying. When I gave 4, it is telling me a negative value. When I give 105, it is telling me 2. 2 does not implicate that he will buy the products twice. All of us are in the same page, right? 2 does not tell us that he buys a product twice, or minus does not tell that he will give a money for not buying a product. None of them are right. Which means this particular approach, what we used for prediction, is giving you some prediction, but we are not able to use it, or rather the result of this prediction is really not telling me anything. Why? Let's see that. Why is it not telling us anything? Let's see from a graph. All that I will do is I will go ahead and plot both of them into a graph. What I am doing, I am using a simple scatter plot from my matplotlib, because for matplotlib I have given an abbreviation value as plt. If you see here, my matplotlib pyplt has been abbreviated as plt. Therefore I have taken a scatter plot and a line graph. Let's try to see from the age and bar how this linear regression has been applied. Now, if you see this particular thing, a very interesting thing. I have given 2 different colors, or rather 3 different colors. The values are in black. The data which we have is in blue, because 0 and 1s are the data. So if I also show you the Excel what we have, let me go ahead, filter here. If I see, it is either 0 or 1. The age can be anything, 1 to whatever. Here it is zeros and ones. So my data, the blue lines is either at 0 or at 1. Now for a minute, let me do this. Okay. Now if you see, this is what is the data scatter. It is all at zeros or ones. There are so many things which you can read out of it. You can say predominant people between 0 to 20 are not at all buying, or large set of people between the age group 0 to 20 are not buying. There are few pockets of people around 6 years, 10 years, 12 years, they have bought a product. Between 20 to 35, either you don't have a data or they have not bought at all. Between 40 to 60, evidently people have bought, because your data set is saying 1, and there are scanty sets of people who are between this age of 40 to 65, they have not bought a product. That the moment you see a scatter plot, you are able to infer that. Now that we have used a linear regression on this data, if you go ahead and see that particular fitment, this is how you see the data. This is a linear regression. Y is equal to mx plus c, what you would have read. We have used the same linear regression and done the fitment. And now if you see, our first age prediction was 4 years. Come here. Where is 4 years? This is 0, this is 10, this is 4 somewhere. If you see here, that is why it is coming it as negative. The second age group what I picked was 105 years. 105 years what I took was somewhere outside the boundary. Therefore, this picked up outside, which is why you have the reason which is available here. So this is what was available here, and when you said 4 or 105, it always returned a value which was unrealistic. Let's see, if I give a value between 10 to 50, will it give me anything relatively fine? Let's try that. I give 55. It is telling me 0.98. One good fact is it is between 0 and 1. Unlike what we saw, minus number or above 1, this is between 0 and 1. And if you see this particular thing, the without the linear regression, somebody had a question saying that can we see the complete scattered plot for all the values? This is what is the complete scattered plot for all the values. Because why you are seeing like this is the plot is based on 0 or 1. Therefore, you see the blue lines only at 0 or 1, unlike your linear regression of other values which are continuous. If it is continuous, you will see the data spread in between. In this case, the data spread is not continuous. Therefore, you will see the data only like this. You will not see in between. Okay. Now, if you see this particular thing, this is the line which you fitted inside the things. Now, age part is showing 60, correct? If you go to your Excel, the maximum age what you have, the data is only 65 years. Till 65 only you have age. You don't have any age data which is above 65. Therefore, in your report also 60, and this is the 65 which it is showing. There is no 70 years. Right? That is the reason why the graph is showing only till 60. Now, why is it giving -2 for 105? A very interesting question, right? I took, see, my data with regard to the store is available for only this many people. These are the people who have visited my store where I have captured the data. But all that I am trying to use this linear regression is tomorrow a person who is age 90 or 105 years, if he walks in, whether he or she will buy a product or not buy a product is my question. So that's why I took the extremities. From that point of view, I used 105 years of age. If I had taken 35, 40, then we can see the things. Okay. Now, this is my age. This is my prediction, or rather whatever I had in my Excel, which is my bot. This is my bot column, which is my Y. X is my age. Okay, got you. Now, here when we saw it for 55 years, when we see this as the prediction, it is telling 0.98. What we were discussing is, even though this is not very appropriate, we needed an answer as 0 or 1. It is not telling me 0 or 1, but it is telling a value between 0 and 1. Unlike in my extreme cases, for 4 it is telling me a negative number. For 105 years it is telling me a value which is beyond 1. Here it is telling me a value which is within 1, which is the probability of a person who is aged 55 to buy is very high. You can say it is 98% probability. So if you see, where is 55? 55 years is here. So it is telling 55 years, most of the people who have walked in, there is a 98% probability that that person will buy. But it is not telling me for things which are outside this range. Here below 10, above 60 or above 65, it is failing. So 55 was just here. See, for 61, if you see here, or 65, let's see here, it is telling 1.19, which it fails, which means till 60, wherever the line cuts, it has a valid answer. But after the line which got cut, the prediction goes for a toss. And for this reason, linear regression will not work for a prediction which is discrete in nature. So there are two ways of learning. One way of learning is to understand what it can solve. The second way of also learning, which is equally important, is what it cannot solve, or what we call as negative testing, right? What all it can, where all it can fail, we should know that also. Which means, in this case, a linear regression has a capping that the prediction can happen only for continuous values, but not for discrete values. Binary or discrete, it cannot happen. So from that perspective, we cannot use linear regression in this approach. So for that perspective, we have to use logistic regression. So what we will do is, we will just stop here. We will take a quick bio break, and we will resume back. We will start talking on logistic regression. So we will take a quick bio break. I will keep the session like this going, and we can come back and start on how exactly for the same data logistic regression is working. Okay.
Oh, sorry, I was on mute. So now, if you see, we did see the graph and we did understand, though the entire process of doing a model and the fit, there is some gap, which means all of that what we did, theoretically it is giving you the values, but it is not serving the purpose. So if you go ahead and analyze the model, what we choose is not right. There is an issue with the type of dependent variable. In this case, there are only two dependent variables. There are only two variables, right? One is the age, one is bought or not bought. Therefore, when we say in this case, age is an independent variable, bought or not bought is a dependent variable, and that dependent variable is of binary nature. It is not continuous. So we cannot fit a linear regression line to this data. If not linear, okay, we are concluding that linear regression is not a right fitment for this because of the above three challenges. It gave the value, it is not giving me the required inputs. If not linear, what else? We say linear regression is not, then what else? So in this case, what we saw, continuous variable between 6 and 80, by 0 is yes, 1 is no. That is how this data came in, which means when we saw this graph got fitted, this is how it got fitted, and this is where within the range between this 15 to 55, you still have some quotient of prediction. Outside this, it fails miserably. So we should see, whenever we have a prediction for such instances where the dependent variable is non-continuous and discrete, you have to not use linear regression. Like gaming, winning or losing, there are only two things, right? You can win or you can lose. Buying or not buying, response or no response, default or no default. In operations, attrition versus retention. In a website, click versus no click. In a fraud identification, is it a fraud or a not a fraud, or a cure or a no cure? These are all discrete areas. They are not continuous, they are discrete. So for such real life scenarios, you cannot use linear regression, which calls us for one other types of regression, which is the logistic function or logistic regression. But what we will see is, before even getting into logistic, we see what are all the other available options with us. There are so many non-linear, then why only logistic? What is the significance of me telling logistic? See this. These are all some your high school content, like a polynomial function, Gaussian function, quadratic function, exponential, sine, double exponential, logistic. These are all few of the options which are available to us, which we can still consider. But let's see what was our intent from this data. Where did the data of prediction fall between? If you see, polynomial is minus n to plus n. There is no higher limit or lower limit.
while in a Gaussian, if you see, this is between 0 to n, while in quadric, if you see, it is also between minus n to plus n. Exponential always starts between 0 and goes above in unidirectional aspect, while in sine, you know how a sine behaves. While if you see logistic, it is between 0 and 1, and it is of shape S, or what we call as logistic function. Many people call this as S graph, S shaped graph also. So here the value is between 0 and 1, and also helping us to say how the prediction can fade. So that is one of the reason why between so many available nonlinear functions, logistic function is one other approach of regression we use when the data is discrete. So what we do as part of logistic function, probably we don't do a lot of changes. We change our linear regression to a small extent, which means what was a straight line cutting through your data, now that straight line is converted as an S-shaped curve. If you see, previously it was like this with an inclination. This inclination, whatever is above and whatever is below, gets reoriented into an S shape. The function of doing such mapping is your logistic regression. Now it becomes meaningful prediction whenever we have certain ages. So for example, if I pick an age of 18 years, now it has a prediction at no. In this case, it has a prediction of yes when it is 55, 60, 62, right? Which means I converted, or rather the logistic function converted the straight line into an S graph. This approach is your logistic regression. There in linear regression, we say y is equal to mx plus c, which is a formula for straight line, and we use the same thing for our linear regression. When it comes to logistic regression, we derive the formula for our sigmoid or logistic function through this statistical means, which means we want a model that predicts the probabilities between 0 and 1, and that is S-shaped, right? So here when we see y is equal to e exponential by 1 plus e exponential of theta becomes your S or sigmoid line of regression. That way we try to predict the probability instead of direct values. So y becomes binary. X is a function which is independent, and y which is dependent is a relative function of your independent value, which is x. So that is how we try to see this. Now we saw that theoretically, which means in simple words, we are converting a straight line into an S shape. Let's see how exactly the logistic regression works when I have to see it in my application using the libraries. Okay, let me take this. Doing the same thing. Basically, I changed my uh, I did not change my data. I just re-imported the same because I had an idle time. Then I imported the same, the bot, the age. Then I used my xplot, used my namespace, line space. Sorry, name not namespace. I got this particular graph. Instead of this, let me use the logistic regression instead of my linear regression. Now, all that I have to do is here in my linear, I use OLS, which is ordinary least square function, where I pass my bot and my age. Instead of that, I use the logit function from my stats model. SM we set stats model on the top, right? If you see here also I have done this. So I have imported stats model.api as my SM. Okay. So now here, if you see the logistic regression for age and buying, I have fitted using the logit, same bot, same age. I've done the fit, and I also get summary like what we got for linear regression. It says 467 observations, residuals, the pseudo r square. All these are some of the relevant matrices which are needed for logistic regression. Now I have done a fitting using logistic regression. Previously I had done using the linear regression. Now let's go ahead and predict the same 4 years, 105 years and 55 years. The three things what we had considered. Let's go ahead and do. I have used age 1 as 4. I use the logit predict. Let me see what does this prediction tell me. What was coming as negative for 4 years now is coming a positive value above 0, just above 0, 0.0023. Let's also see for 105. Just below 1.999. See for 55. 0.9937, 0.9999. This is 0.0002. What is it telling me? Even though it is not telling me 0 or 1, but it is giving within the range. And if I round it off, I will be able to conclude saying that a person of 4 years will not buy, a person of 105 years, there is a higher probability of buying. person of 55 years, higher probability of buying. The same thing, if you happen to see it from a pictorial representation, let me copy all of this. I will run one by one, that way we will know what is happening. Okay, now first I scatter my x and y, which is 0 and 1. Next I go ahead, same data what I showed initially. I will plot the linear regression, which did not change. Next, I will plot the logistic regression prediction, what we just did, which is predict, linear, predict. See the graph. The blue ones are the data points. The red line is the linear regression line. The green line is the logistic regression line. We converted the red linear line into a logistic line. That's where, when I show you the prediction for 4 years, 4 year comes here somewhere, right? It is nearing 0. The 105 comes, this is 60, this will be 80, 100, 110, which means it comes somewhere here. All these are yes. Therefore, when I say 55, it gave me here, which means theoretically we converted the output which is readable, meaningful, decideful. That way we got our answer. Here, when it is giving us a value which is 0.99, 0.93, it is the probability. And being a stats rich library, stats model, it is telling you 0.99, 0.88, 0.16. But if you use more commercially viable library such as scikit-learn, it will automatically round this off and give you 0 or 1. We will see that as well. Here it is indirectly telling you I have a probability of 99.999% of percent times this person will buy. There is a small probability that he may not buy. While if I use the scikit-learn, let me also do that. I will explain the code. If you see, one other way to fit the model, where what I say is, from scikit-learn linear model, I am importing logistic regression. I said it is available in part of linear model, right? That's what we saw in the documentation. That's where we saw, and I got it, that particular library to be imported. Now, what I see, logistic is equal to logistic regression, and fit, I'm passing two variables, the age and the bot, whatever we have. In this case, very limited data, so I have passed both of them in the same thing. Now I go ahead and run this, which means I am using the same data. I am using a different library, which is the ExcelR library rather than the stats model library. And this is my result for various attributes. I don't have to do really anything. What it is telling me is, whichever are the other parameters which it required, it has passed the default parameters, and it is telling me a summary. Okay, now Let's use the same thing to predict the same 4 years, 104 years, 105 years and 55. What I did, I have 4. I am doing the logistic predict based on this model. See the way the answer comes. The moment I gave 4 years, it said 0. If I pass 105, it says 1. Unlike my stats model for 105 gave me 0.998, here it is saying 1. We will see the 55 years also. Which means from an end user perspective, a ExcelR library is more refined to give you that holistic reply whether the prediction is yes or prediction is no. While if you are more a data scientist or a machine learning engineer, especially for your regression models, try to model that from stats model, see what are all the gaps, understand the scope for refinement. The refinement can be at a model level, a data level, or at the approach level. Then you can use your ESK learn. So that way you know how exactly things are getting molded, what exactly are getting transformed, and where is the result oriented action which is coming in. This way you can do things relatively easy and very well. Okay, the problem does not stop here. The problem in our case of this data, we have taken only and only 2 variables, which is a simple logistic regression with 2 variables. But if I happen to take a data set which has multiple line items like this, I have taken a data set which has multiple columns, a fiber bits data, where if you see I have some 6-7 columns or more than that, right? 1 2 3 4 5 6 7 8 9 10 9 columns at least, right? So what is this data set? Typically it is, this is a internet or ISP provided data set where I have some fields like whether it's a customer who is active or not active, what is the income as disclosed by the customer, months on this network, number of complaints what he has raised, then number of times he has done the plan change, whether there was a history of relocation, what is the monthly generated bill, technical issues reported per month, and speed test result. Which means unlike our previous data set, the data here is higher. Now if we have to predict something, let me take what is logical here. You guys can ping me. What is logical here? What can I predict? Number of plan changes, monthly bill, technical issues. From a regression standpoint, what all pointers I can predict? I can predict so many things, right? I can predict how many complaints a given customer can raise, how many times he might do a plan change, or the most bigger one, will he remain active on my network, or is a person who will switch out from my network, which is active or not active. So what we will see here is, let's try to see how we can incorporate multiple attributes into a single logistic regression, which can help you and influence that particular thing. Now, I am using the same stats model. I have my Y where I want my prediction. I have my X, which has various other attributes like income, months on network, number of complaints, all of this. But before this, I will also have to read the data. Let me read the data. Okay, so if you see, it gave me what are all the columns, and if I see, for example, fiber. So if you see, I get this. If I say fiber dot head, I get some values, or rather always I will prefer sample. So I got some values. Let me put 10 values. So this is a large data set. If you see, some 60-70,000 records are there. 83,959 is also there. So a good amount of data is available, unlike our previous thing which had very limited data. Now with this amount of data, let's go ahead and do the fitment. Now all that I'm doing is, it did a fitment with reference to all these attributes: income, months on network, complaints, plan changes, relocated, technical issues, speed test result, all of this. Simple one line, I got the answer. Now what we are seeing is, if we are seeing this particular thing, we also have the ways to predict, right? If I see the summary, it gives me the summary like what it gave me, and I can use my predict functionality both at the stats model, or if I happen to do the same thing like what we did using our ExcelR. Here I am using the ExcelR X and Y, which I had previously defined here. My X, my Y. This is one line which is using stats model. Here I am using my scikit-learn model. Now if I see this,
If I see this, it is telling me if I push this particular predict, it is telling me where all I have the risk of retaining or losing the customer, which means this is an approach of multi factor logistic regression. That way we can go ahead and do that whatever we have and how exactly we can do the things. So this gives us that background of how a logistic regression works. And like your linear regression, logistic regression also supports multiple variables. It is not about one to one, it is one to many. You can have multiple independent variables and one dependent variable. So that is how your logistic regression comes into place. This gives us a very holistic understanding on what is logistic regression. And we see the data is getting molded based on the simple approach of logistic function. So what we will do here is we spoke about the regression aspects. With this, we will have to start about decision tree. What I will do is I will not start decision tree completely today. I will give a very small gist and we will talk in detail about a decision tree tomorrow. So decision tree by its virtue is an approach to help you decide what you need. So if I happen to put a thought process, or if I say till we reunite tomorrow for the session, if I happen to give you a simple holistic example, it is like you visiting an ice cream parlor. In an ice cream parlor, you have a various options of ice creams, at least 10, 15, 20, 40, 50, based on the size of the ice cream parlor you go. So many varieties you have, but you will never end up eating all of them. You will buy one among them. Now the problem statement what I need you to think, which I will explain you in detail, is how do you decide what will you eat, and how will you decide what you will not eat, right? This give a thought, and I can help you understand the whole approach of decision tree exhaustively in our tomorrow session. We will go unbox what is decision tree, how decision tree will happen, and then you can get the whole things of happening. Okay, so with this we will conclude our session today, and we will resume back tomorrow same time on decision tree. Okay, thanks everybody, thanks for your time.